make sure to get consent from everybody. But it's just me in the room. All right, so tonight we're going to look at chapter 2. We're going to look at organizing data. We're going to look at a ton of different graphs, box or not box and whisker plots, actually. Seven leaf plots. We're going to look at bar charts. We're going to histograms, pie charts. Most of this stuff, again, just like chapter 1, you probably have seen before in some way or sense. A lot of the stuff with the graphs, every day you see graphs. So it's like you're going to recognize some of the stuff. We're going to go into a little bit more of the vocabulary and things behind it. So this way you can start seeing the mathematical terms that go along with it. You'll understand the difference between a histogram and a bar chart because they look very similar and people confuse the two of them quite often. So we'll look at the difference between those as well. So and then at the end, we're going to look at a whole bunch of horrible graphs and you're going to tell me what's wrong with them. All right. I'm going to actually shut off both lights right now. Just a little bit. Can everybody see fine? Okay, that looks a little better to me, at least than before. So. If it gets too dark, I'll turn on the light, but at least for right now. All right, all this stuff is in the book, so if you have the book, you can easily look at it there as well. So I know some of the font's a little small because copying and pasting from things. So, and unfortunately, I can't make it any bigger on the screen. So the first thing we're going to look at is the difference between like variables, and then we're going to look at data. When you think, so now this is a math class, so when you hear variables, what do you think of? Okay. Not necessarily the mathematical term for it, but that is something, yes. Yeah, typically when you think about variables in math, you're thinking about unknowns, right? And actually in statistics, it's more closer to what you're things that differences, things that vary from people to people or data sets to data sets. So that's what you're going to be thinking about when in terms of variables in this response. There's two different types of variables. There's a qualitative variable and a quantitative variable. I know they chose two Qs, which makes this a little harder to remember. Qualitative are non-numerical terms. So hair color, eye color, the type of pen you're writing with, things like that. Those are qualitative, okay? Because it's not numerical. Quantitative, think about quantity, that is numerical, right? So age, birthday of the month. Like you can actually, believe it or not, birthday, like the entire thing would actually more become qualitative because you can't necessarily do calculations on it. But the day of the month would be qualitative or quantitative because you can start doing calculations or sort those. So some things, depending on how you use them, can be a little blurry there. Most of the stuff that we're going to work with past this point will be quantitative because we're going to be doing calculations on it. All right. But we're going to look at some stuff tonight because doing graphs and stuff, you can do that stuff, qualitative data. Another two things you're going to see is discrete versus continuous variables. So a discrete variable is one that only has a certain number of possibilities. Now, a discrete variable actually can be both qualitative and quantitative, all right? Because so like hair color, there's only a certain number of people, different hair colors you can have. I know that's growing greatly with dyes and stuff like that, but eye color is the same thing. There's only a certain number of eye colors you can have. So those are discrete variables because there's a specific number of them. On the quantitative side, heights. There's yes, it varies between it, but you're typically not going to have anybody 9-10 feet tall. There's an upper limit to it, and then there's a lower limit to it as well. So you can have quantitative or qualitative there. Continuous variables cannot be qualitative. They have to be quantitative. Yeah, quantitative. Because continuous variables mean that every single point in between them also would work. Okay? So, amount of money you have, because that could be anything from 0 to infinity at that point. And every decimal in between that also would work. Things like that would be continuous variables. Those are going to come into play when we start looking at the graphs, because when we're starting to look at like histograms and bar charts, if they're continuous variables, we can do them a little bit differently. We can set up the charts a little differently because the points in between it actually matter. And that's actually, let me see if I can find one real quick while I'm thinking about this, because this is a very good graph to start looking at. Let's see. Yes, this one. Copy image. All right. So what kind of graph is this? Oh, no, not. Just forget the actual names. What kind of graph is this right now? If you saw this graph prior to today, what would you have told me it was? A line graph, right? All right. Now, we'll go to the second part of this question. Is the data, the actual x-axis at the bottom, is that qualitative or quantitative data? Yes. It is qualitative. They're actually specific names of games, right? Okay. And the side is telling you how many people are playing those on a specific day. All right. So now now the question is this continuous data, or is this discrete? Is this a continuous variable or a discrete variable? This would be discrete. There's very specific values to it. Okay. And that's what makes this a horrible, horrible, horrible graph. Every single one of you, I guarantee, at some point in the past made a graph just like this. You put some dots on it, and every time you see dots on a graph, you connect your dots. Okay? Whenever you connect the dots, the line between it means something. The line between it means those values between those points would also exist. Okay? Which would make it continuous, not discrete. Is there anything such thing between poker and blackjack? No. So that line there means nothing. So there should not be a line on this graph. Okay? So that's one of those things that once you put a line between things, and you're going to be making line graphs throughout this entire class. You're going to be doing stuff like this. When you put a line between 2 points, that line has meaning, and it means that all the values between those points still exist. Okay? So just keep that in mind. We're going to look at a lot of bad graphs. This is a horrific graph, and it drives math teachers nuts when people do this. I've seen like administration and stuff like that do graphs like this. It's like, I wish I could go back and find some of the old pie charts and stuff that my administration used to do. They're really, really bad. But yeah, keep that in mind. That's a big difference between discrete and continuous, is that line between them. All right. Now let's look at data. Just a little bigger. No, I cannot. Not without totally messing it up. So, all right. So actually, we'll talk about the little chart up here. This is just a little, not a bad chart. Variables, you have qualitative and quantitative. Quantitative can be either discrete or continuous in that respect. Qualitative is just qualitative. It's just set of data. All right, data. So we have our variables. Data is the values of all those variables. Okay, so in this graph right here that we looked at, what is one of my 2 variables? I have 2 variables on this graph. What's one of them? That's not one of the 2 variables. The number of participants, that's one of the variables. What's the other one? The game. Okay? Those are 2 different types of variables. The data would be where you're going to get the Wednesdays and the Sundays, the breakdown of those things. So that would be the actual the data, because you're going to have all those different values put in there. Now we have, just like we had variables, we have qualitative data and we have quantitative data. In that graph, the games they're playing would be qualitative data, and the number of people would be quantitative. Sorry, I'm going to mess them up with the two Q's. I really wish they came up with better names for them. All right. So, and again, same thing. We're also going to have your discrete data and your continuous data. So same concept as with the variables. You're not going to have a continuous variable in a discrete data set. If it's a continuous variable, it's going to be continuous data. Okay. All right, so let's look at a couple problems. I actually can make these a little bigger. All right, human blood types. Human beings have one of 4 blood types. And yes, there's a positive and negative in each of these, so technically it's 8 blood types. A, B, AB, or O. What kind of data do you receive when you are told your blood type? Is it qualitative data or quantitative data? Huh? Qualitative, yes. Okay. Household size. The U.S. Census Bureau collects data on household size and publishes the information in current population reports. What kind of data is the number of people in your household? Yes. That is quantitative. Now, is that a discrete data? Is that discrete data or a discrete variable or a continuous variable? Can you have 2.5 kids? No, it's discrete. Okay. Continuous would mean all the values between those points would work. Okay. So even though, yes, you could have 1 billion people living in your house, I would hope not, you couldn't have 2.5 people living in your house. Okay. So it's discrete in the fact that you cannot have all the values between those points. Okay. World's highest waterfalls. The information, please, almanac. Okay. List the world's highest waterfalls. The list shows that Angel Falls in Venezuela is 3,281 feet, or more than twice as high as Ribbon Falls in Yosemite, California, which is 1,612 feet. What kind of data are these heights? They're quantitative, yes, and they also would be continuous. So, because a waterfall could be technically any height, right? Between those values. It might have a top and a bottom, but all the values between those would work. You could have a waterfall that's 32.35 feet tall. All right. So yes, those would be a continuous data set. Okay. All right. Most of the stuff we're going to look at is going to be quantitative data, but we can look at some stuff that is qualitative data too. The first one we're going to look at is with qualitative. So a frequency distribution of qualitative data is a listing of distinct values and their frequencies. So if we go back to that graph that we looked at a minute ago with the line, the bad line graph, that was a frequency distribution for all intents and purposes. They had the number of the people or the game and how many people were playing. Okay. They would have just done a tally or something like that, which is what we're going to look at there. And then they would put it on a graph with the dots. So that was in essence a picture version of a frequency distribution. All right. To construct a frequency distribution of qualitative data, you're going to list the distinct values. And you're going to, for each observation, you're going to place a tally mark in the second column, and you're going to count the tallies. Okay. That's in essence all you're going to do. So you're going to list them all, count them up, say, okay, I've got 5 brown, 3 red, 7 blue, and then mark them off. All right. So we've got this table for Professor Weiss, which happens to be the guy that wrote the book. So he made himself a professor in the book. Asked his statistics class to state the political party affiliation as Democrat, Republican, or other. The response of 40 students is listed below. So the first question I have, I'll make this a little bigger. So what type of data is this? This is qualitative. All right. Anytime you have words, most likely it's going to be qualitative. All right. It's kind of a pretty dead giveaway. Any problems with the way he did this? Ask the question. Reinforces the belief that there's only two parties, but that's okay. More stuff to bug your political science teacher about. All right, let's actually make our table. So we have Democrats, we have Republicans, and we have other. I'm not going to make the tallies, but I will just cross things off. So let's see. How many Democrats are there? You've got one. Oh, you already got them? Thank you. Saves me the trouble. So we've got 15. How many Republicans are there? 13. How many others are there? Oh, that's okay. See what happens when I trust you guys? I get the numbers wrong. All right. How many others were there? 9. 19. 29. 32. Well, let's see. There's only 40 and I got 41. So something's wrong. All right, let's count it. All right, so we got 1 Democrat, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13, that's right. Let's see. Because I don't feel like using red and blue. 1, 2, 3, 4, 5, 6. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Republicans. And then if we count this correct, So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, yes, others should be the difference. However, if you did that when we did the second thing, you would have had other wrong. So when you're counting up data, count all of them. Okay? And then add up your numbers at the end and make sure it comes out to the total you expect. Okay? Because if you had counted Democrats right 13, then you had Republicans in 19, and you said, oh, well, what's left is 8, you'd have had 2 of the 3 wrong instead of only 1 of the 3 wrong. So keep that in mind, especially when you're looking at larger data sets. It's really easy to script your counts.
So you said count them all and add them?
Yeah, count them all. That's what I did at the end. When I added the 3, I'm like, wait, I've got 41 here. Something's wrong because I should have only had 40. So then we went back and looked to figure out where our mistake was, and we found we had overcounted the Republicans. So just something to keep in mind when you're doing it. Now, the interesting thing is if you looked at the actual political, actually, I'll actually find it. So I'll get the actual numbers. Nope. Nope. I want. That works. That's close enough. This is in 2014, but it's at least not that far out of the date. That. All right. We're going to get to this a little bit. What kind of graph is this? Pie chart. Good. Does everybody think this is a good pie chart? Why almost? Does it not add up to 100?
It looks like it's off the scale.
Oh, yeah, okay, yeah. I was gonna say, wait, does it not add up? That's unfair. So we're gonna look at this later when we start looking at misleading graphs, but we're gonna look at a bunch of graphs today, so I might as well put it all together. When you're looking at a pie chart, first thing is they have to add up to 100%. They don't always, based on one of the graphs I'm going to show you later. Independent is actually the largest political party in the United States because it's not actually a political party. It's all the rest of the parties put together. But Republicans and Democrats do not make up that big of a portion of the United States. And this was in 2014, and it's actually gotten worse since then. So when he surveyed his class, that's actually unusual that he had that much of a political divide in the things. Normally, independents or other would have been a lot higher. So, interesting little things. You're going to see, okay, so there they are. You're going to see a lot of graphs that have to deal with government and politics and money and stuff like that, just because that's actually where statistics is used most often. And it's also where statistics is used wrong most often. So it makes really good to have it throw those up as examples. All right, so what did we just do here? What kind of graph? What did we just do? This is a what? This would be a frequency distribution. Okay. And we're going to get rid of that graph so I don't have that over there. All right, so that's all we did. We just did a frequency distribution. We counted it up, tallied them up, and got the number of each one. We have not made a graph with this or anything else. This is just a distribution. We're going to use this data and other problems in a few minutes. So, all right. Now, relative frequency. So the only difference between a frequency distribution of qualitative data is just the count. Okay. Now, here's the nice thing. We can't do calculations on words, right? So we can't do calculations on qualitative data. We can on numbers. So in essence, what we just did here is we took a qualitative data set and we got numbers from them, which we can now do calculations on. So relative frequency is basically taking each of them and finding out of the percentage of them, right? So what's the relative frequency of that specific thing to the total of it? So when we were originally doing, you're going to do the division, you're going to get it as a decimal. Those decimals should add up to 1. When you change it to a percent, the percent should add up to 100. Okay? Depending on how you round, it can be a little off. All right? Sometimes you can get things that add up to 101, or sometimes you get things that add up to 99. That's just a rounding error. If you take it out a couple extra decimal places, you normally can get rid of those rounding errors. So it really just depends on how accurate you want your data. Okay, so relative frequency distribution, get the frequency distribution, and we're going to divide each one of them by the total. So if we look at the problem that we just did, we had Democrat was 13, Republican was 18, and other was 9. So we're going to divide each of those by 40. So we're going to divide them by 40. Since you messed up the count, I'm not going to trust your calculation skills. Take out my calculator. All right, so we do 13 divided by 40. And no, I can't do all these in my head. So 325. 18 divided by 40. 45. And then 9 divided by 40. 0.225. Again, same thing as I said with the tallies. Do all 3 calculations and add them up. Adding them up is your check. As long as they add up to 1 in the decimal, we're good. So if we take those add up, so 0.325 plus 45 plus 0.225, 0.45, we get 1. So we know they added up correctly, so we know we did our calculations correctly. Odds are, if you're going to screw it up, you're not going to screw up more than one of them that's going to then come out to be one. You're probably going to screw up one of them, and it's going to screw up the total count there. So you'll be able to catch your mistakes. Okay. How do I change a decimal to a percent? It's multiplying by 100. So this is 32.5%. This is 45%. And this is 22.5%. So we now have our relative frequency. Depending on how you're going to use it, you could leave it as a decimal, or you might want to change it to a percent. If you're going to do a pie chart with it, you have to change it to a percent. If you're just basically telling the relative frequency, you might be able to leave it as a decimal. It's fine. All right. That's where a lot of this stuff comes down into play. It's what are you using the data for, and how do you want to actually display that data to somebody else? Okay. And that's when we're looking at the misleading graphs at the end is like, what do you want to get other people to get out of your data? And that's where I said at the beginning, statistics is one of the few classes in math you can lie with. So depending on how you display your data, depending on how you do your data, you can show certain things or get people to believe certain ways. So, all right. Now, the best way, and actually one of the few ways that you should ever use a pie chart. Pie charts have to be based on relative frequencies. Okay. So a pie chart is just divided into wedge shape with portions proportional to the relative frequency of the qualitative data. You obtain the relative frequency, you divide the distance into the portions, and you label them. Most of you are never going to actually do a pie chart out by hand, so no, I'm not going to show you how to actually use a compass to break up the thing and the correct things with the degrees and stuff. You're going to use a computer or Excel or something like that to be able to create one. Huh? Yeah, you're not doing this out by hand. Actually, some of the older books, like the older stats book, actually had the breakdown in a specific way to do it on a pie chart by hand. We're not doing that. I don't remember who yes. Yeah, because you need the breakdown of those percentages. All right. You could have a pie chart that shows the specific data set in it, like the 13, the 18, or the thing, but the proportions or how the pies are broken up should be based on the relative frequency and not based on the number that you've given. So, which is one of the big things that people do wrong with pie charts. All right, which I'm going to show you a couple in a minute. All right, so here's what the pie chart would look like. So you got 45% Republican, 22.5% other, and 32.5% Democratic. All right. Colors don't really matter. Just make them that they're distinct in the graph. You don't really need graphs that are very specific in their colors. All right. Let's see. Let's use this graph. All right. All right. This is what kind of graph? Pie chart. Is it a good pie chart? Okay. So what's wrong with it? Okay, there's no percentages. But we just said we didn't necessarily have to have it as percentages, right? We said we could have put the numbers there. So the question is it proportionate, proportion-wise, right? So we have, so that's pretty close to $1 trillion. Is that 1/10 of this? Might be pretty. Because that's where you're going to start to get into the messy. So, like, I specifically chose this one because I wanted you to see that there was no percentages. It wasn't broken down like that. There's no real connectivity between the actual three things. They're also all over different time frames. One's every a decade, one's over 3 or 2 years, and then one's the student loan cancellation thing that they're doing. This is another one of those graphs that they're showing to evoke a certain emotion or a certain response from. Right? They're like, well, we can give $300 billion away for giving $10 trillion to the military. It's that type of graph. So these are the types of things that when we're looking through the stats and we're starting to go through and do the calculations and starting to understand what's going on, you want to start to get a little more of a keen eye on it, right? You want to be able to understand what they're trying to get out of when they're showing you this data. You want to be able to have that critical thinking and ask the questions on, okay, what's the purpose of this? Who's putting it out? Why are they doing it? Where's the data coming from before this point? All right, so this way you can start, and you will understand, you can go back and look at the data, start to be able to understand where that data came from and be able to draw your own conclusions from it instead of what somebody's telling you to think. Okay? They say a picture's worth 1,000 words. That's why, because nobody wants to read the 1,000 words. All right? They want the picture because it's easy. But if instead of reading the 1,000 words, you might get a very different viewpoint than if you just look at the picture. So when we're looking at some of this stuff, that's where you want to keep your mind going and stuff. All right. All right. A bar chart. Now, even though so far all the graphs that we've done, the pie chart, the relative frequency and those things, you can do those on quantitative data as well. We're looking at it in terms of, because these graphs work for qualitative, but even though it works for qualitative, you could do quantitative calculations on it as well. All right, we could count up the age of everybody in here, which is a quantitative piece, and do it the same way. Figure out how many people are between certain points and stuff. All right, so a bar chart. A bar chart displays the distinct values of the quantitative data on a horizontal axis and the relative frequencies or percents of those values on the vertical axis. So to construct a bar chart, you obtain the relative frequency distribution of the data by applying what we did before. Draw the horizontal axis, or each distinct value, construct a vertical bar, and then label those bars with the distinct values. So let's go back and look at my horrible graph that I hate. If we were to eliminate, so I'm just going to look at the purple one. If we were to eliminate the line in between, and I just did this, that's now a bar chart, which would actually be a better representation of the data than the way they did it. And they could even do a double bar chart because the Monday, the Wednesday, and the Sunday, you could easily have the other bar right next to it. And I'm horrible drawing. Actually, you know what? I forgot. I can use the trick. If you ever want to draw straight lines on a computer, hold shift while you're drawing it. Even with the mouse. If you hold shift and draw it with the mouse, it'll actually give you a perfectly straight line. So you can easily have the double bar graph with the two lines there. That's fine. All right, but that would be a better representation of it as a bar graph instead of how they did it with just the dots and the lines. Okay. Now, did they use the relative frequency there, or did they just use the frequency? So were those, so the numbers on the left side are just the frequency, right? They didn't do a calculations on it, figuring out the difference between them. Bar charts can be done either way. You do not necessarily have to have it in terms of a percent. All right. What you do need, though, is you do need your graph broken down equally. So notice how this graph, 0, 1,000, 2,000, they're all broken evenly. The bars are separated evenly. So the graph that's at 7,000 is approximately 7 times higher than the graph that's the bar that's on 1,000. Okay. That's important. When we're doing relative frequency, the same concept has to happen. You want it broken down by the percents evenly distributed over the vertical axis. Okay. All right, so here is our bar charts. Again, not making you do this out by hand. Nobody does this stuff out by hand anymore. Bar chart's actually pretty easy to do by hand. That's not that big of a deal. They did do this in relative frequency. And the key with this one now, are they separated out evenly going up? Okay. Let's see if I can do this really quickly. I'm going to try to do something really quickly. This is what happens when I think of things while I'm in the middle class. I'm like, ooh, let me try that. 0.45. Oh, that was Republican, not Democrat. Who was Democrat? 22 point. No, Democrat was 32.5, right? 325 and other was 0.25. Okay. Yeah. All right. Okay, so we've got this graph. That's my quick graph on Excel. Except that I switched the Democrats to Republicans. It's the same data, right? Okay. I'm going to make one change to this graph, and then I'm going to show it to you again. Plot area. All right. Is the data the same in these two graphs? What did I change, if anybody can actually see it? Okay. So this one goes from 0 to 50%. This one goes from 0 to 100%. Does it give you a different viewpoint? Okay. I didn't change the data. Data's the same. This one looks a lot closer between the different parties, where this one looks a lot bigger. All right. So this graph right here would be considered a misleading graph. That is completely accurate. They've expanded the vertical axis, or they've changed the vertical axis to change your perspective on things. Okay. So that's one of the big things they do with bar charts, is they will change those vertical axes quite a bit. Okay. Both are correct. Both are mathematically right. Both are done. The data is right, but it changes perspective. All right. All right. Any questions with what we were working with, the qualitative data? Those are really the only two types of graphs you can do with qualitative data. Is pie charts and bar charts. Okay. All the other graphs that we see need to be quantitative. Okay. All right. So we're going to look at three different types of grouping. So the first one is called single value grouping. This is very similar to what we just did a minute ago with the frequency distribution. All right. Television Bureau of Advertising publishes information on television ownership and trends in televisions. Given the number of TV sets per household for 50 randomly selected households. Use a single value grouping to organize them into data into frequency and then the relative frequency distributions. So, here's an interesting question. Has anybody ever actually been a Nielsen family? Not the Nelsons.
No.
Nielsen's actually the people who actually tell you what you watch on TV. So if you've ever, when they talk about this was watched by 40 million people or 18 million people, or was this share of people 18 to 25, those things, that all comes from the Nielsen group. And what they did, and I'll get in trouble if they ever hear that I said this. So I was a Nielsen family at one point. Remember what I said? If anybody ever calls you up and asks you things on the phone, answer it because you can get things. What they did was they actually had a box that would attach to your TV when people used to only have one TV, and you just press who people were watching it. And they would monitor what was on the TV and say, okay, you're watching CBS or ABC or NBC and stuff like that. Now, what they do is they actually have a little, it's a little beeper device that actually listens for, so every TV show, inaudible to you, actually has a signal in the background that tells you what channel it's on and everything else. Same thing on radio stations and those things. So what this beeper does is it picks up those signals, and they're designed for each person. So every person in the house has one, and it'll tell exactly what they're watching. So if you've ever had your favorite TV show canceled, it's because there's like 500 people in the entire United States that does this, and they didn't like that show. So it's like, if you get the chance, do it. It's actually kind of interesting. It works now even with like Netflix and all those other things. Because again, every show has that embedded in it because those places want the data from Nielsen. So it's built in automatically to be able to give them that data so they can actually say, yes, this many people watched it. The nice thing with a lot of streaming services now is you can actually see people download it and whatnot, or they can count as you're viewing it. Problem is they don't know how many people are physically sitting in that room doing it. So this actually gives them more of that actual data and not like the type of person that's watching it. Like they don't know if you're 18 to 25 or 25 to 30 or whatever else it is, where the Nielsen data would actually be able to give them that information as well, which is used for advertisers to sell you things. All right, so single value grouping. We're going to do exactly the same thing as frequency charts. So we're just going to count up how many of them there are. All right, so this one looks like I have all the numbers from 0 to 6. I think it's the biggest one. All right, so we're going to 0, 1, 2, 3, 4, 5, 6. And I don't think I have the answer on the other screen. I do not. So we're going to count them. All right, so let's go through and count them real quick. So we've got 1, 1, 0. 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12, 13, 14, 15, 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 2, 3, 5, 6, 7, 8, 9, 10, 12. 1, 2, 3, 3. 1, 2, 1, 2. All right, let's see if they added up right. 30, 40, 2, 3. Yes, we got 50. All right, so we've counted them up. That is a what? Is that a frequency or relative frequency distribution? Not yet. That's just a frequency distribution. How do we make it a relative frequency distribution? Yes. Divide by 50. If it's getting dark over there, let me know and I can turn the set of lights on. So It's like the screens kind of help things, and I'm not sure how well you guys are seeing. So, all right, nice little trick when you're so we have 50 of them. How many times does 50 go into 100? Twice. So if you just double all the numbers, there's your decimal. So this one's going to be 0 or 0.02. This will be 0.32, 28, 24, 6, 4, and 4. So if you're ever going to get data and collect data, collect it in multiples of 50. Make sure life's a lot easier to deal with it. All right, that's now relative frequency because in essence we divided each one of them by 50. Okay, so frequency distribution is just the count. Relative frequency, we have to compare them to the other ones. The nice thing about doing relative frequency is it allows us to compare data sets. So say you did this part, had 50 people, and you guys did it when you got 225 people. The counts would be different. So the counts wouldn't be useful. However, if you both came up with relative frequencies, we could compare those percentages. Okay, so that's where you want to start looking at the percentages and why we go back down to the relative frequency. All right, so that is single value grouping. The next thing we're going to look at is limit grouping. So limit grouping is when we group them by a specific number of values. So in this case, we're going to group them by tens. Okay. So if I'm going to group it by tens, what's the smallest number here? See a 38, 36. I don't see any 20s, so 36 will be the lowest one. All right, so if we're going to group these by tens, yes. That's going to be my question. How would you want to break this up in tens? Do you want to do 36 to 46? And then what would be the next one? Okay, so there was one, I was hoping you'd say something different after I said 36 to 46. If you did 36 to 46, what would be the next one? 47 to what? Okay. When you're doing limit grouping, the one thing you don't want to do is overlap. So you don't want to have 46 on both of them. Okay. Now, how many numbers are between 36 and 46? Count them. 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46. I've got 11, not 10. If you wanted to do this, you do 36 to 45 as your breakpoint. But why make your life hard? 30 to 39, 40 to 49. Okay, make life easy. They didn't tell you had to separate it out specific ways. So do it nicely. I know. Is there any? Yes, there's 90s. And there's no hundreds. So there you go. Okay. There will be certain situations when we start looking at them that you actually want to do classes where you actually have to do the specific values. Okay. But if it just says do groupings of 10, make it easy for yourself to count. All right. Now I don't even really have to look at the second number. I just have to look at the first one. But that will actually change. Like if you were going to graph this and stuff like that later, that would change how your graphs look too, depending on how you do it. So again, it depends on how you want to separate things. All right. So let's see, 30 to 39. So we've got 30. So we got 1, 2, This is where the math teacher would actually have done much better to actually have done all these calculations ahead of time and have them already on the screen for you. But nah, let's go them out. We got time to kill. 40s. And since you guys can't count correctly, 1, 50. Nope. I'll forget about that next week. All right, let's see. 1, 2, 3, 4. Because if I make a mistake, you guys aren't going to let it go either. 5, 6, 7, 8. I got 8 there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 5, 6, 7. 1, 2, 3, 4. And we had 40 of them. 4, 12, 22, 36, 40. Counted correctly. All right. Is that a frequency distribution or a relative frequency distribution? Frequency. How do I get the relative frequency? Divide them all by 40. And I'll just do it. Sorry. All right. What's 3 divided by 40? Okay. All right. What's 1 divided by 40 is 0.025. 8 divided by 40, 20. 10 divided by 40, 0.25. 7 divided by 40, 0.175. And 4 divided by 40 is 0.1. So 0.10. That's now relative frequency. What makes this different than the last problem when we did the single value grouping?
Range of numbers.
It's a range of values. That's where the limit grouping comes in. This is the first thing that cannot be done on qualitative. Okay? This can only be done on quantitative data. Right? You have to have numbers to be able to do this. Okay? All right. So limit grouping has a few things that keep in mind. We have the lowest class limit and the upper class limit. So in the problem that we just did, the first one, 30 was the lowest class limit, 39 was the upper class limit. We have the class width. Class width in this case was what? Nope. The class width is how big the classes are. So in this case, my class limit or width was 10. Okay. And the last one is the class mark. This is actually really important because if we're going to do a bar graph with this or a histogram, the bar charts, a lot of times they'll put the rate, they'll actually put 30 to 39 and stuff like that on there. Histograms, they typically will not, but you do not have to. You can use a class mark for it. So instead of putting 30 to 39, you could put 35. Or actually, it wouldn't be 35. It'd be 34.5 because that's exactly in the middle between 30 and 39. Okay? Most of the times your class marks will end up being decimals because you're having the average of two numbers in there. So a lot of times it will come out to be decimals, and that's fine. If you're also doing the lower in class limits and the upper class limits, you want to make sure that the values don't overlap, like we said before. So that's where your upper and lower class limits can never be the same. So, but a lot of times you'll see the class mark there, and those will be the values we'll put on the graph instead of the whole range. Doesn't mean that every value is that. It just means that's the number between those two values. All right. All right, so I'm gonna actually move this up. So this is the weights of 18 to 24-year-old males. There is to the nearest tenth of a pound. So when we're looking at cut point groupings really come into play when you have decimals and stuff like that. It'll definitely help you out there. So, but the process is very similar to it. So this one, they want you to use a class width of 20 and the first cut point of 120. So we're going to make this a little bigger. So what would be my classes? So my first point is 120, right? And I'm doing it to, what do we say, 20, right? So what's going to be the next break? $139. Okay, 1 second. The screen that was on kind of froze up. All right, so in the last problem, where is it? There we go. If I did 139, would that eliminate values that could possibly be in that grouping? We're doing it to the nearest tenth, right? You could have 139.2. Yes. Well, no, we could definitely do 120. Like that's fine. We want our class width to be 20. So 20, the value of 20 would just be technically anything under 140, right? Because even if I did 139.99, it's fine. So we wouldn't actually want to put the 139 there. Because this is decimal, because this could be continuous data, all the numbers under there would work. So you'd want to do 122 under 140. That's how you actually write it. So this way you don't have to necessarily write all the decimal points. Since this is one decimal point, if you did 139.9, that technically wouldn't be wrong. It would still work. You'd be able to include those values in there. But by writing under 140, you don't have to necessarily worry about that. All right. And since I don't feel like actually going through and counting all this out and writing all this down, I have the table. We're just going to paste it in there. I'm getting tired of counting. All right. Put this on the next slide. Everybody can read that, right? All right, so here we go. So you can see how they broke it out. 120 to under 140. There was 3 of them. There was a total of 37 values. So 3 divided by 37 gives you 0.081. Then you go 140 to under 160. 160 to under 180, so on and so forth. Notice how when they added these up, does it come out to be 1? No, it comes out to be 0.999, right? Which is pretty darn close, right? Remember what I said. There are little rounding errors in there. Okay. If you got 0.999 or 1.001, I wouldn't overly worry about it. It most likely is just a rounding error. It's fine. Okay. You're not going to go out to that many decimal places for most of the stuff you're going to do anyway, so it's fine. And if you rounded, if it was 2 decimal places, that would round to 1, and you'd be fine. So this right here is known as the cut point grouping. We have same concept as the limit grouping. We have an lower class cut point and the upper class cut point. Now, the lower class cut point is, again, the smallest one, so it'd be 120. The upper class cut point is the smallest value that could go into the next higher class. So that's where it's under 140. All right, so the upper class cut point is 140. It's just underneath that. Class width, same thing. It's the difference between the 2 cut points. So if you subtract 140 and 120, you get 20, which was what we wanted. And the midpoint is, again, the same thing. It's the average of the 2 cut points of a class. So between 120 and 140, it would be 130, would be the midpoint of that one. All right. All right. So we've got 3 different group methods, and sometimes you're going to have to figure out when you'd want to use them. Single value grouping, anytime you have discrete data and there's only a small number of distinct values. All right, single value grouping is no different than what we did with the frequency distribution with qualitative. All right, so same concept. You're not going to want to do it if you have 1,000 data points. Okay, it's just not going to happen. Unless there are only numbers from 0 to 5 or something like that, then you could definitely count it up. But single value grouping is typically very small data sets and not a lot of variability, not a lot of different values. As I say, distinct values. Limit grouping, you want to use when the data is expressed as whole numbers, so there's not decimals in it. And again, there's too many values to be able to use single value grouping. All right. And then cut point grouping is when the data is continuous and are expressed with decimals. So really, the only difference between limit grouping and cut point grouping is the decimals. Once you get the decimals, you have to go to the cut point because you need all the values up to the next one. Where in limit grouping, I could cut off at 139 because I know there's not going to be a 139.5. And that'd be fine. That's really the difference between those two. Okay, they look very similar. They're very similar in how you design and do them out. It's just that one little distinct difference. Okay. All right. We're not done. But I am going to give you a little bit of a break. About 10 minutes, go to the bathroom, get water. I have to switch over to my next slides anyway. Here. Congratulations. Yes. Just watch the video afterwards.
What page is it on?
Let's see. According to my online book, I have 113. Oh, okay. That would be why online books don't always group great. I was like, I literally that's what it says at the bottom of my page. It seemed a little high, but what's up?
We're going to the first class description after.
Gotcha. So everything is on bakersmathclass.com. Syllabus is there. Actually, the video from the last class is there, so you can watch through that. So it's just bakersmathclass.com, and I'll show you actually real quick. So and just click on statistics, and there you go. Cool. So
And
there's the
then-
syllabus in that.
Can we just use the online textbook, or do we have
Yeah,
to
that's
like, in person?
Nope.
That's fine.
Yeah, online one's fine.
Okay.
And if you're doing that, you go to 113 because that's what my online book tells me. I don't even have an actual physical book of this class, so.
So you were saying bakersmathclass.com. This is my first class, actually. I added this class.
Okay, so yes, actually, hold on a second. I will show you the screen while everybody's
I checked the,
Yeah, I don't use Blackboard.
and I saw that there was stuff in there, but it was on,
If there was anything actually on Blackboard,
it was just like the skeleton.
yeah, I was gonna say it would have been just literally the.
All the categories.
Yeah. All right, so here is Baker's Math Class. Really straightforward, simple, easy to get to. It works on all your devices, which is great. You just click on statistics, and there's the stuff for statistics. There's for the class. So there's the syllabus is right there, and that's the recording of last week's class.
Perfect.
So
Wow.
next week's class, or after I go home tonight, I'll post the video. If it's not posted tonight, I'll post it tomorrow morning.
But we just like Baker's Math.
Probably way more straightforward than Blackboard.
Yeah.
Because it's all just in one string.
Way simpler. And the nice thing is it's always there.
Okay.
So
Yeah.
it's like if 2 years down the road you go back, I remember that from that class. Let me go back. The videos and everything else will still be there.
Yeah.
So you could easily go back and look. Like all my stuff for my calculus class is back there for 8 years.
You have the book.
I do not have the book. Oh yeah, I do not actually have a textbook. They gave me the online version, said, here you go.
It's not.
Yeah.
I don't know if you have $200 drop like that, but.
Lucky for me, this is my third try with this class, so I already have the book.
God. All right, so we're gonna make sure that you do not have a fourth try with this.
Yeah, well, I've had a lot of other extemporaneous things happen in my life.
Okay,
Really drew away from my ability to go to the.
gotcha. Not a problem.
I'm here for the long haul this time.
Listen, I'm just bad at math, so I came into this class expecting to fail.
So
It's not so bad if you actually have the capability of sitting down and doing the work.
I was gonna say, honestly, first of all, I don't have a very high failure rate to begin with. I know it seems that way when you say, well, you only got basically your entire grades 4 tests in the final. So some people freak out about that.
Scary.
But I always review before the final. I mean, always review before the test. So you'll know exactly what's on the test. Which definitely helps. The nice thing about this class compared to most other math classes is it's not very algebra heavy. You're going to see some formulas and stuff like that, but a lot of it's going to be plug and play. As long as you can use your calculator, we're good.
Well, I just the last math class that I took, I was in the IB program at the high school.
Yep.
And it was a 2-year course, but then in the middle of my first year, and we got stuck with COVID, so my teacher didn't teach anything. And then for my entire senior year, he just sent like 3-hour videos out. I didn't have 3 hours, so I didn't learn a single thing. My best friend did all my homework for me, and I passed the exam with a 3 somehow. I somehow passed it.
But hey, that's the exam.
I answered 3 questions, so I guess the 3 questions I answered were right. There was like 27 questions I answered right.
Can you do a preview for the exam the week after also, or do
So,
you find out that's better for the same thing?
so what I'm going to try to do,
Okay.
because we have a 3-hour class or a 2-hour, 2.5-hour class, what I'm gonna try to do is the class before the test, I'm gonna review for probably the last hour of the class,
Okay.
and I'll practice test. The next class, the test will be at the beginning of that class, and then we will start the material after the test.
Okay.
That's my plan.
Okay, good point.
It might end up being that the next class is just the test. I have to look at how it is because I do want to review before, not the same day. Because I know when I originally set it up, I was going to review and then you're going to take the test. I'm like, that's just not going to work.
No, because if we like not doing something good, like we want to have time to practice.
Exactly.
later.
Yeah. So this is the first time in many, many years that I've actually had a 1-night class. Most of the class have been 2 nights. So after I did the syllabus, then I'm like, that's not going to work. So yeah, I think that's going to be my plan is to do like an hour or so of the class before the review for the test. I'll have a review test. So I will typically create 2 tests. They're basically the exact type of thing. So for example, if I'm going to choose the even problems for the test, I'll probably choose the odd problems close to it. So they're similar problems. You'll get the, it depends. It really depends on how long the questions are.
I don't know how
If-
long to be stuck in here for.
So that's the thing. So I have to figure out exactly how I want to do the test. So if I'm going to do the test and then have you guys do some work after the test, which I really don't like that option, but depending on if I'm going to be able to fit what I need to fit in, I might have to do that. If that's the case, then your test should take you about an hour, maybe an hour and 15 minutes, because I want to do about an hour or so class after that point. What I do when I create my tests, I will typically create the test. I will take the test. I used to double the amount of time I took the test, and that was how much time I'd give you. I'm up to about 4 times now, which is fine. So I would look to take the test. If it took me about 15 or 20 minutes, that's about how long you should take about an hour or so to be able to do the test. That's about what I'd be at. For 2 reasons. 1, I'm getting a lot better at it, so I can do it a lot quicker. And 2, it just seems to be, I don't know, it's over the past 25 years, it's like people have slowed down in how they're doing things. And I don't know, there's a lot of reasons for that, but it has definitely taken students a lot longer to do some things than it has in the past. So, which is fine. These tests are probably going to be a little more reading heavy than a typical algebra test because, again, they're word problems, they're data sets and stuff like that. It's not going to be, here's a problem, solve it. It's going to be, here's the data, come up with a chart for me. Or here's the data, what would be the class sets? Like I said, I'm not going to have you do out pie charts and bar charts and stuff like that by hand. But you might have to do like the relative frequency table so you can show me those things out. And then you tell me what the pie chart's going to look like. Like what are the 3 pies in there? What's the percentages for each one? Those type of things. So it really just depends on the type of questions and how many questions there is. Because some of those questions could take you 15, 20 minutes to do. So I might only have 5 or 6 questions on it, where another test, you could go through it a lot quicker. I might have 15 or 20 questions on the test. So it just depends on the breakdown of it. And I won't know that until I actually go through and make the test. So one other thing while I'm thinking about it is typically, since there is 4 tests, if you do poorly on one of the tests, you're like, oh, great, I'm dead. One of the options, because the final is a cumulative final, one of your options to make up a test is your final exam. So you can, as long as you do better on the final exam than one of your tests, I will automatically replace the test with the final exam. So let's say you got a 40 on one of your tests, but you got a 70 on the final exam. That 40 becomes a 70 for one of them. So it'll replace the lowest test grade, which typically tends to help a lot of people out. There also might be an opportunity, depending on how people do for, like, especially statistics for a project, to make up some extra points. If you wanted a test, that's something we can talk about when we get into it. Yep.
During the day, right?
So I'm not here during the day because I teach high school, but I can be here on Tuesdays and Thursdays after my classes then. Yeah. So my classes on Tuesdays and Thursdays are from 5 to like 6:15. So I can be around after that point.
So I took a day off from work last Friday to come here to see a tutor.
Yeah.
And go to the tutoring
So,
center, and they're booked out for
okay.
weeks.
So here's the second option. The wonders of technology. We can set up a time, as long as I don't have to physically come here to do it, I can do it online too.
Okay.
And I have a full touchscreen that I can write on everything else. So literally it would be no different than that type of
Because I
stuff.
also work 9 to 5:30, so that won't.
Yeah, that would, yeah. So, but yeah, we can, if you need some time, we can work things out, depending on what I'm doing on the weekend, maybe it's Saturday night or Sunday afternoon or something like that. Yeah. Just let me know.
I'm gonna let you know now.
Okay. Well, let's see. This Saturday I'm working in Norwalk, so I can't do Saturday. And I have to check with my significant others about Sunday.
Okay.
Just send me a quick email. Say, hey, these are a couple times I'm available. What works for you? Okay. Yep, I'm literally gonna. I'm not making these problems up. Yep, most likely the tests are coming from the evens. Problem is the even ones, the answers aren't in the back of the book, so you can't check your work. Oh, they are. Oh, there you go. So yeah, so I'm probably gonna pull most of mine. Most of mine are gonna come from the evens because the answers weren't there. But if you do the odd ones, they parallel pretty well. So like number 5 is probably very similar to number 6 or number 4. So it's like you can look at it that way. But like I said, I create 2 tests. One's the review, one's the test. They're almost identical. So if you can do the review, you should be able to do the test. And remember, I do allow a note card. I don't remember if I told you guys that. So when you're going through and doing the review test, if you need to start looking stuff up in the book for those tests, write it on your note card. Like, that's the easiest way to do it. Because if it's needed on the review test, it's probably going to be needed on the test. All right. So,
That's 4 by 6.
yep, 4x6 is fine. So, yeah, you can grab them at Staples or the dollar store or whatever else. Both sides, fine. Yeah, especially with this stuff, it's like there's a lot of like definitions and things like that. So
I read very small. for
That's
paper
fine.
like that. I have like a 5 by 7 for my science stuff one year, and I literally was able to put the entirety of chapter 2 on that So.
funny story. So when I was in school, my professor stated that we were allowed to have one sheet of paper for our final exam. And I said, no problem. So this is one of the reasons I don't let you use paper. So she allowed one sheet of paper. Now this professor, because the nice thing is when you're in a regular school, you get the dorms and stuff like that, you get to know how the professors are. Well, this professor, all of her final exams came from all the questions from her regular tests. So she took different questions from her tests and put them on the final exam. Her tests, she gave back the answer sheets for every one of her tests after she did it. So in essence, you had every single answer of the test that was on the final exam. So I went to the photocopy machine and I shrunk every single answer sheet that she had given us and put it on one sheet of paper. So I had every single answer for the test. So that's why I do an index card, because you're not going to throw those through a copy machine, and it typically has to be handwritten. So, but yeah, you can write as small as you want. It just has to be in your handwriting. So, but yeah, so it's all the crazy things that I did at school. I like the index card for the other reason, because like I said with the test, when you're going through and doing the review test, you're going to write down stuff that you need. So it gives you that practice of being able to say, okay, I'm going to practice. I'm going to look, this is something I need. Let me write it down. Instead of just have your book, have your notes and everything else. And you're not going to study because I have everything. Why should I study? And then you go to the test and you're spending 90% of your time flipping through your books. Like, where is this? Where is this? And you're going to run out of time. So the index card kind of forces you to study, which I think works really, really well. So that's why I do the index card. All right. Can you guys still see back there? Or do you want me to turn on the lights? Okay. I'm like, I like it dark. So as long as you guys can see, I'm fine. All right. Let's see. Where were we? This one. All right. Okay. Next set of problems. Histograms. So histogram, actually, I'm going to do this way. I'm going to make this a little bigger. I can't make this any bigger. That's a problem. So a histogram works really well for single value grouping and limit and cut through grouping. So we're looking at these are now looking at quantitative and not qualitative. Okay, so these have to be numerical in value. So for single value groupings, you're going to use the distinct values to label each bar. For the limit grouping and cut through grouping, you can either use the lowest class limits to label the bars, or you can actually use the midpoints of the class marks, or actually use those breakpoints too. Most of your technology, like your Excels and stuff like that, unless you tell it otherwise, it's going to use the breakpoints. It'll use like the 125 and things like that in between the two values. So to construct, I think somebody I put the histogram there. Oh, good. Yes. All right. I was like, I made sure I copied those in there. So to construct a histogram, because we're not making these all up. So the first thing you have to do is obtain the frequency and distribution of the data. You're going to draw your horizontal axis to place the bars. For each class, you're going to construct a vertical bar. And then you're going to label the bars in the classes. You might think, well, that's no different than a bar chart. The big difference is, first of all, a bar chart can use qualitative data. All right. And the other big thing is, a bar chart, the bar shouldn't touch. Okay? Because in a bar chart, they're distinct values. In a histogram, those distinct values show a range of data. Okay, and those ranges do touch. So your histograms should touch. So we have the television sets per household. This was a single value grouping that we did. You've got your, notice the dashes in the middle are representing that bar. This is the frequency, and then we have the relative frequency. They look very similar in those respects. This is a chart on short-term investments, which was, I don't know if we did this problem or not, actually. Oh, yeah, we actually did. This was the one we counted up all the numbers. I just didn't remember what it was. So this is the frequency. Notice how in this one, they did use the 30, the breaking that down by tens. They actually start off at 0. Notice the bar is between 30 and 40. Okay? Those are my lower and my upper class. Remember, we went from 30 to 39, then 40 to 49. So the bar stroke is between the 30 and the 40, not centered on the 30 and the 40. Okay? So we could have written it that way, or we could have done 30, 35, 45, 55, and stuff like that, put it in the middle of the bars. This is just the relative frequency of that. And then we have the weight one we did. What's one of the things that you notice about the weight graph that's different than the other ones? It doesn't start at 0. Because it doesn't start at 0, make this a little bigger so you can see it. They put those 2 little dashes right there. That signifies a break. You could do those 2 little dashes. You could do a little squiggly line just to designate a break point. You do need to have something there to designate that you did not go to 0, because the default is that the graph goes to 0. And otherwise, that first bar would have been 0 to 120, which would not have made sense for this data, because your data, your set classes should always be equally distant.
And when there's a break with nothing, there's just no data.
Right. Yeah. Exactly. So we started at 120. We didn't need 0. So they just showed up the break because they said, okay, we're starting at 120 instead of 0. Okay. You can, and we're going to see a graph a little bit later that has a break in the graph. There's a reason for it, and we'll talk about why and how that can also impact viewpoints. Okay. All right, so those are histograms. Does everybody understand the big difference between a histogram and a bar chart? Because those two are confused all the time. So bar charts can be used for qualitative data, not just quantitative. Bar charts are typically separated, and the value underneath it is that specific for that bar. All right. Histograms, you're looking at ranges sometimes. It is all quantitative data. You cannot do this with qualitative. And the bars can be between values because they show ranges, which is what we see here. Next, dot plots. A dot plot is a graph in which each observation is plotted as a dot at an appropriate place above a horizontal axis. Observations having equal values are stacked vertically. So when you're constructing it, you're going to draw the horizontal axis, record each observation by placing a dot over that value, and you label the horizontal axis with the name of the variable. Looking at that, what's missing that we've had in every other graph except for the pie chart? We have a horizontal axis. What do we not have? You do not have a vertical axis. Okay? So a dot plot does not need the vertical axis because you would discount the values, the number of dots. It literally is designed to be counting. So here is an example of a dot plot. So these are prices of DVD players that nobody buys anymore. So see, yes, DVD players are expensive. when they first came out. We have between 190 and 230. You don't have every single value there, but the values have to be broken down equally. So in this case, every one of those lines is 1. So we have one value at, this is 197. And we have 3 that were at 199. So it's again, like I said, there's no vertical classes. Yes.
I work in retail, and I actually had a guy come in and ask me if we sell DVD players today.
Well, that's better than a VHS player.
But I work at Tractor Supply,
Oh, jeez.
so I don't know how he got the notion that we might have a DVD player.
The crazy thing is, if you went to like Ocean State, I actually think they might have
They
them.
might have them.
That- Yeah, I wouldn't think Tractor Supply.
It's a good thing we were in close enough proximity to Best Buy to walk there. So.
Yeah, they probably still have them.
Yeah, I would go for that.
Yeah, it's like they still have them. You can still use DVD players. It's not normal. Like if they came in and asked for, a VHS player, totally separate conversation. I would like. I understand the vintage like vinyl and like records and stuff like that. Anybody who actually wants a cassette player or a VHS player never lived in the 90s and the late 80s and never had to deal with them getting stuck. Like that was the one nice thing about a record or a CD. It couldn't get stuck. It could skip, absolutely, but it couldn't get stuck. I had to rip out too many tapes out of VHS players. I took electronics at the tech schools, and that's one of the things we had to do was repair VHS players. Never do I want to have to do that again. So when DVDs came out, that was a very nice movement away from the tape-based process. But yeah, maybe at some point VHS, like cassette players are coming back. Like they're selling cassettes and like Walkmans and stuff. Like really? Yeah, it's like not something I want again. All right, so those are the prices. That's a dot plot. Pretty simple, straightforward. One of the nice things about a dot plot, when we're looking at a little bit later on, we're going to start looking at the normal distribution of the bell curve, where the dot plots actually will show that type of thing. So if you actually like pour sand into a thing, it'll actually form a nice bell curve. In essence, each of those grains is just like a dot plot. It actually will form that type of mound. And that's actually on purpose. All right. Next one. Stem and leaf diagram. Anybody ever? So pretty much up to this point, has anybody not heard of any of those graphs before? Maybe the dot plot, but all the rest of them you guys have seen before, right? How many people have actually ever seen a stem and leaf diagram before? Okay, so a few. Not bad. At some point, we're also going to look at a box and whisker plot, which is also another very interesting graph. Those actually show a lot of really good information. And once you learn how to do them, they're actually pretty easy to do. Stem and leaf diagrams. The goal of a stem and leaf is actually to almost do what we did with the limit grouping. It's by tens. So the whole number, like the tens column will be the stem, and then the leaves will be the numbers after it. So this is a stem and leaf plot. So each of the values there. So like if you look here, all the threes, the first I've got a 38 here. So I've got 38. I've got 36 here, so you got a 36. Then there's a 39 somewhere. There's a 39. So I got 39. All right. So in essence, I'll also put these up on the website too. So, but you're more than welcome to take a picture of it too if you want. So the stem and leaves, you can start to look and see how it actually starts to group that data. It's also very similar to those dot plots, except they're not individual data points. They're now they're grouped, like the limit grouping that we did. Your stems, the stem will be everything except for the rightmost number. So if we were doing hundreds, it'd be 130, 140, 150, 160, those type of things there. You can do multiple stems. So let's say you had data, and actually, I think I have one of those. Maybe not. Let's say, like, if we just ignored the first three, and we're just looking at 6, 7, and 8. If I just looked at that one stem, it wouldn't necessarily be as impressive. But if I sit there and split these up, so now I'm going to show this is going to be from 60 to 64, and then 65 to 69. Those things. We might be able to start getting more granular in there. You do that when you don't have as many 10 groupings. You start grouping them by 5, for example. So stem and leaf is just broken down like that. Again, we're starting to look at, and we're going to go into in a minute, we're starting to look at the design and how the data is formed. So the nice thing about stem and leaf plots and dot plots, you can start to see like an actual like curves forming. So if we look at our dot plot here, you're going to have like an actual curve forming. You get the more data you get, the more distinct those curves are going to start to be. Same thing with the histograms. You have those curves forming. So if you start to look back here at the histogram, it goes up and then it kind of tails down. All right, this one kind of goes up and comes down about the same. So you can start to see those curves forming with the data. All right. Who can tell me what this is? This is a bell curve. It is the most used shape in math. Pretty much all data, when you get past 30 to 50 data points, will start to form some kind of a normal distribution. This is going to be, if you're like this class, your friend. If you hate this class, the bane of your existence. Because pretty much everything we're going to be doing past this is working with this. We're going to look at standard deviation. We're going to look at mean mode median. We're going to look at hypothesis testing, and all that is based on this little chart here. So you can start to see the middle, or the median, is where the majority of your values are going to be. If you've looked at this at any time in the past, you probably talked about standard deviation in 1 standard deviation, 2 standard deviations away from the mean. Within 1 standard deviation, you don't have to write this stuff down. We're going to do this way more, but it's nice to introduce it. Within 1 standard deviation of the mean, you'll have 67% of all your data. So 67% of everybody is within 1 standard deviation of a mean of height. 2 standard deviations is 95% of the people. 3 standard deviations is 99.7% of the people. So if you're outside of 3 standard deviations away with it, you're like at the 0.03% in the population. Anybody work in construction, engineering, things, how tall is the doors in buildings? Anybody know?
I don't know about the doors. What, 7? About, yeah, I would say 7 or 8. 7.7.
78, or actually they're 80 inches tall. Okay, which would be 6 feet 8 inches tall. Okay, that hits 3 standard deviations away from the mean of the average height of a male in the United States. Okay, so that means that basically 3 out of 1,000 people might hit their head walking through the door. And actually, not even 3 out of 1,000 people. Sorry, I take that back because it's 3 out of 1,000 on both ends. So about 1.5 out of 1,000 people. So 15 out of every 10,000 people would hit their head. That's huh?
The third guy ducks.
Yeah, they'll just duck.
Yeah.
So that's actually how they start to design things. All right. They look at the standard deviation. They figure out, oh, okay, this is going to fit the majority of people because the taller they make it or the shorter they make it, it's going to cost them more money. All right. And everything comes down to money. So if they have to go up to 80 inches or 90 inches, it's going to cost them more money and they're going to have to do everything else around it. So that fits the vast majority of people in the United States. So we're good. Okay. Same thing with weight limits on boats and weight limits on elevators, all this other stuff. They all use that calculation for it. So they go into the elevator and it says 10 people are 2,000 pounds. It's because within standard deviations, 2,000 pounds would be about 1,200 pounds a person, and that would hit the vast majority of people. All right. And I'll probably end up telling the story again at some point when we actually start talking about boats. Now, so there was a boat accident in New York a long time ago, and the boat had a capacity limit of a number of people, and it was like 30 people that could fit on this boat. They didn't have a weight limit; they just had the capacity. They said 30 people. Normally, not an issue. Okay, because they have a variety of people. Well, there happened to be a bachelor party that came into town with like 30 people, and they had like 25 of them went on the boat, all bigger guys, capsized the boat. They were under the limit. They only had 25 people on the boat. They did it based on averages and assumed a certain percentage of those people would have been female, which would have been lighter, and would have balanced it out. But by they had 25 larger guys on there, capsized the boat. So that's why they now put capacity limits and weight limits on them, because you have to think about it both. So it's like little things, and that's where we're just going to start talking about statistics and using it. It's like those are the types of things that this comes into play. How many times have you ever had a warranty expire like a week or a month before something breaks? That's on purpose. All right. They didn't design it to break. However, they know that after 18 months, the percentage of issues start to increase. So the warranty is 18 months. Because after that point, they're going to have more and more issues. Before that point, it's within a realm of acceptable risk. So that's literally by design. Things will start breaking after your warranty expires.
They can sell it for.
Exactly. That's where Best Buy makes all their money. So yeah, never buy an extended warranty. It's really just not worth the time. Unless you're driving a lot, and then buy the extended warranty on your car, because that saved me money actually. So it's like those are the types of things to think about. And those are why those things exist. So that's one of the things that I really hope you get out of this class, is to start being able to understand those things and the math behind those things and why it happens that way and those things. So this is the bell curve. This is the normal distribution. All right. Modality. When you think of mode, let's think way back. So you have mean, mode, and median, right? Or mean, median, and mode. What's mean? Mean is average, right? Mean and average are the same thing. You add them all up, divide by how many you have. What's median? The middle. So why do we have, so technically, a lot of times mean is your middle. And if it's normally distributed, your mean should be your median, or very close to it. If it's not, however, they will separate. What's the difference between mean and median? Why would we use median over mean? Yeah, so your median doesn't get thrown off by there you go. It's like I have the word, it's out something. Outliers. Yeah, doesn't get thrown off by those outliers. All right, that's why we talk about median a lot of time, especially the income and home prices and stuff like that, because it's not going to get thrown out by the $100 million house on the island in the state of Connecticut to throw the values off. So yes, there really is a house in Connecticut that's $100 million. What's mode? Yeah, mode's the one that appears most often. Mode is also the only one that we can have multiples of them. Now, modality is similar to that. The reason I brought it up is because modes, you can have multiple ones. A unimode, you have one. it's going to only have one major hump. Okay. Your normal distributions can fall at this. They'll be skewed left or right or center. Your normal distributions will never be bimodal or multimodal. They'll never have the humps that go up and down. However, data can. All right. So, bimodal, you can have a split in it. Multimodal will just be a crazier looking graph. Most of the graphs that we're going to look at are going to be more unimodal because that's what your normal distributions are. Symmetry. When we're talking about the distribution of a graph, symmetry is really important. We have the first one is your bell shape. That's your bell curve. Like I said, you're going to become very familiar with bell curves. The difference between a bell curve and your triangular one, although they do have that one peak, your bell curve, notice there's a lot more in the middle. That's where you get your 67%, 95%. Your triangular is more of a linear progression. So it's not necessarily going to be, the values consistently go up instead of go up quicker as it gets to the middle. And then you can have your uniform where everything's basically the same. All right, skewedness. This one's actually important. The other two, you're going to see more bell curves, but you're not going to see very much as triangular. You might see some stuff that's uniform, but with the bell curves and with normal distributions, you can have right skewed or left skewed. So right skewed and left skewed, basically, remember I said that in a bell curve, your mean and your median should be basically the same right in the middle? Your left and right skewed is where they start to move. Okay? So a right skewed, this is your median, right in the middle there. Okay? Your mean is going to be somewhere over here. It's going to be pulled to the right. All right? It's going to be pulled to the right because you have some outliers over here that are pulling it that way. Okay, so the majority of your data is here. That's why your median is down here. But since the mean is pulled to the right by those outliers, it's right skewed. The reason I'm pointing that out is if you look at this, most people are going to say that's left because you're going to look at where the hump is. Okay? You're not looking at where the hump is. You're looking at where the data is being pulled to. Okay? So since this data is being pulled to the right, it's right skewed. This one, same concept. Your median's over here. Your mean is being pulled to the left because your outliers are lower. Okay? So that's why it's left skewed. So the other way you could think about it, the way they said it was, which one's tall? Which one's bigger? The tail. Is the left tail bigger? Then it's left skewed. If it's right tail's bigger, then it's right skewed. Okay. All right. Couple more definitions and stuff, and then we'll get into some fun little graphs, and then I'll get you out of here. All right. We talked a little bit last time about population and sample. So population is the value variables for the entire population. Okay. So, and that's something that when we start looking at calculations, you're going to need to know if you're dealing with the population or the sample because the calculations change a little bit. All right. So population is everybody. Sample is a subsection of that data. It's a sample of the population. Remember that sample has to be randomly acquired, not just one little group of it. The distribution of population data is called the population distribution, or the distribution of the variable. And then, of course, we have the sample distribution. Those are going to change when you're looking at it. So we could do our bell curve of a sample data, but then we're going to use that bell curve to make inferences about the population. All right. Any questions on any of those before we do some fun things? And somebody shaking their goes, math fun? No. All right. Misleading graphs. All right. The lovely unemployment rates. All right, both these graphs are the exact same thing, the exact same data. So one of the biggest things, so when you're lying with statistics or trying to sway somebody one direction or another, you don't want to fudge the data, right? You want to use data that's accurate. Okay? Because if you use data that's inaccurate or wrong, you're going to get called out. All right. However, if you use a misleading graph, first of all, the majority of the people that are going to look at that graph aren't going to notice it. Okay? Because they're not looking that deep into it anyway. They're just looking at the picture and the headline. All right? Because you're looking at it quick. You're scrolling through Facebook or Instagram and you're just looking, and there's a picture and a little description and you're done. You're not clicking the link to read the entire article. All right? So that's what they're trying to get. So these are both unemployment rates. What's the difference between the two graphs? Okay, so really the data is the same. The difference is the horizontal or the vertical axis, right? So the vertical axis in the first one is from 7% to 8%. The vertical axis in the right one is from 0 to 8. Okay. Question is which one's misleading? One.
Because it shows it's a lot closer than the one.
Okay. So, I guess it depends on your perspective, right? If I'm the politician in office and I want to show that unemployment rate is dropping and we're doing great, I'm going to show this graph. Because that shows that it's dropping. It can drop that much, a couple percent or a couple tenths of a percent, right? But it dropped, right? If I'm the politician that wants to show that unemployment really hasn't changed, do this graph. So you can start to see how they use them. Neither one's wrong. Technically, if you think mathematically, this is actually the misleading graph because we're starting at 7, we're not starting at 0. And they did put the break point. If they had put the break here to show that the graph had stopped, like we didn't go all the way down to 0, and they would actually just do a break all the way across, that would be fine. And then that graph technically wouldn't be misleading at all. Okay, because there's a visual reminder that this graph does go all the way down, except I'm just not showing that, and I'm showing you the most important part of the data. Right? Because like this one, you lose a lot of detail. Like you might want that detail. It's like, unfortunately, unemployment rate doesn't drop that much anytime. So a 0.1% here, a 0.1% there can actually make a rather big difference when you're talking about millions of people. So, okay. That's where Facebook puts lacks context. It's not inaccurate. There's other information that they need to tell you about it. All right. Over 100 million now receiving federal welfare. All right, so this was the graph. These are old graphs. This is back in 2011, so this is an old graph. Is this a good graph or misleading? Where's the graph start? Starts at 94, but what's the first quarter at? So like 97 million? Quarter one, this one over here, was like right about 97 million. And quarter two in 2011 is about 107. So it went up by about 10 million, right? But looking at the way that graph is going up and the headline, is anything mathematically wrong about what they said? No. There is more than 100 million people that are now receiving some form of welfare. And it did increase. However, if we're looking at this bar compared to that bar, right, you're going to get the impression that it went up gangbusters. Okay? Because again, a picture's worth 1,000 words. They're not looking at the numbers. All right? Society in general is very math phobic. So we've had these conversations already in here. All right? So when you see numbers, black out the numbers, let me just look at the picture. But you lose context. Right? And that's what the goal of this article says. There's a lot more people on welfare. Yes, there was another 10 million people. That is a lot. But based on the picture, not that much more. Okay? It was about a 10% increase. And if you look at the bar to the bar, that would look like probably about a 4 or 5 times increase. Okay? All right. USA Today is awesome for their graphs. They really are. I loved USA Today's graphs because they were always horrible graphs. All right, here we go. Common injuries children suffer. What's wrong with this graph? All right, so it's hard to read. What are those percent? So,
I'm not telling you how many children for that percent.
okay, so let's look at just the first one. 5.2% have spinal injuries. If I'm looking at this graph and I don't really read everything else around it, I'm like, oh my God, 5% of kids have spinal injuries? No. It's only 5% of kids with traumatic orthopedic injuries, which are hospitalized, have spinal injuries. Not 5% of all children. Okay? Or 21% have a thyroid. Like, that's just massive amounts of people. Yes. Kids are getting injured. A lot of times it's with the legs because they did something stupid and jumped somewhere. Or they fell off a bike. That's where your arms come into place. So in reality, let's shrink this back down. The real figure is approximately for the spinal fractures was 0.0000003% of children have a spinal injury. Okay. However, if they told you that, yeah, it's not big of a jump. I can live with those odds. Okay. But 5.2%, scary. Correct. And if you think back to how they were producing a ton of the numbers for COVID, you saw a very similar situation. The death rate was off the roof. But if you look at the death rate compared to the entire population, it really wasn't that bad. Yes, a million people dying is a lot of people. But when you're talking about 375 million people in the United States, your chances of dying are very slim. And I think I mentioned it was like if you look at the children has a more chance of dying in a car accident than of COVID. Yet everybody are petrified of COVID, not of the car accidents. People are driving like nuts on the highway now. It's like, it's crazy. Yeah, like I drove back from New Jersey on Saturday, and it was like, I swear to God, I was going to get hit 3 times. Like, the car was flying. I'm like, what the hell? Like, I was shocked one guy actually stopped behind a car. I'm like, you had really good brakes, because there's no way I expected you to be able to stop that fast. It's just nuts. So it's like, but that's the thing. You have to take things into perspective. We've already tied, like, the whole car accident thing and everything else We've accepted that as part of a risk of driving. So when you think of the COVID and other things like that, we haven't accepted that risk yet.
And it would be like an airplane.
Yeah. It's like it's accepted. It's like we know it's a very, very small percentage, but we know it could happen. We don't stop flying for it. But you get 2 or 3 plane crashes showing up on the news, people start to get nervous and freak out. So it's like, and yesterday was 9/11. When they calculated in all the deaths from 9/11 that year, the percentage of plane deaths was extremely high. But you had to look at context. So it's like if you looked at a graph when you had that in there, you're going to see the spike. And it's like if you don't have the context, you're not going to understand why that spike was there.
I'm a
Lo-
9/11 survivor.
Where you at?
My husband, I was in New York yesterday.
Huh?
My husband was on the 93rd floor in Tower 1.
I'm sorry.
So I remember after 9/11, I didn't actually fly me and my children didn't fly until 2008.
Uh-huh.
I was refused to get on a plane.
Yeah, I don't blame you. I don't blame you one bit. It's like it's one of those days that anybody that was alive will never remember, or will never forget. And the crazy thing is, so now I teach high school. It's 21 years ago. The kids today weren't even born. Yeah, there's quite a few people or alive or just born.
I was 4 months old.
Yeah, so it's like it's crazy.
I was 29. My husband was 29.
I was 24, and I was literally in front of a classroom when it happened. And I remember I had the only TV in the building that actually worked, that had a signal, so I could actually get it on. So I actually had so all the teachers were running down to my classroom to see what was going on before they released us. So it was a crazy day. All right, let's look at more crazy graphs before we get going. So, anybody remember Terry Schiavo? All right, so it was a case in Florida. This woman, if I remember right, her husband didn't want to her husband didn't want to euthanize her, but her family did.
Oh, yeah.
It was one of the two. I can't remember which direction it was. But the court had sided with the one to keep her alive. Actually, let me rephrase it. The court, because based on these numbers, I know it went the other direction. The court decided to let her be pulled the plug. Yeah, life support. So this is the graph that came out. Democrats, 62%, Republicans, 54%, Independents, 54% agreed with the court. If you look at that graph, just the graph and forget the numbers, do you get that same impression? No. You're going to get that the majority of Democrats agreed, but most Republicans and Independents did not. But we're starting off at 50%. Like, we're starting off at 50%. Like, it's literally an 8% difference. But this was to push an agenda. And you see this a ton. Okay? So when you're starting to look at graphs, especially bar graphs, they do this with a ton, is look at the numbers on the side. Don't just look at the bars. Okay? All right, my favorite, I don't mind Fox News, I really don't, but them and USA Today were my favorite when I came out with graphs. Here you go. What's wrong with this pie chart?
It doesn't add up. It's over 100.
First of all, yes, they're all the exact same. It's well over 100. It's almost 200%. Yeah, like.
Oh my
It's like not a graph, not data used for a pie chart. The pie charts look pretty. Right? So it's like, yeah, this should not have been a pie chart at all. Yeah, a lot of money. Yeah, most administrators would do things like that. They love pie charts. Give me a pie chart. You can't make a pie. Give me a pie chart. Okay. They love pie charts, but yeah, that's again. Exactly. It tastes good. All right. Let's look at this graph. This is another interesting. So job and health insurance losses are accelerating. So this is the unemployment rate, and that's the uninsured Americans. So what do you notice about this graph?
That's the correlation.
It does. And back in 2007 and 2009, there really was a correlation. Like most, and actually even today, most people get their returns from their jobs. I think that needs to change. Don't necessarily agree with how they're changing it, but that definitely needs to change. Because you shouldn't have to stay at a job just to keep your insurance, which some people have to do. What else is wrong with this graph? Okay, so it doesn't start at 0. Okay. So look at the right side of the graph. There's another vertical axis. And it also doesn't start at 0. But it also varies a lot more than the one on the right or the one on the left. So this is one of those graphs that, again, the data is right. But if these both started at 0, it would not necessarily show the same impression. When you're looking at multiple lines and having multiple axes, that's also a very bad way to look at things. All right. They could have easily showed uninsured Americans and the number of unemployed, and kept it in millions. They could have easily done that. So, or made them both percentages. You could have done that. So it's like, as long as they're both comparing the same way and looking at the same, you can start to see things. But by looking at two different values in two different ways, it doesn't work as well. All right. Hold on. I want to make sure, because I thought I had one more cool one. So I want to make sure. All right. What's wrong with this graph?
It's a mirror.
It is. And looking at the actual data, should it be? It should basically mirror mirror image, right? As approval goes up, disapproval has to go down, right? Because you can only, the only thing that would be different in there, and that's why it's not an exact mirror, is there's some people who are unsure that they just didn't put in there to make it add up to 100%. Because 68 and 28 does not add up to 100%. It adds up to 96. So there's a little variation there. But is what's wrong? Is there anything wrong with the graph? It does go from 0 to 80. It starts at 0.
I'm looking at the years, but I thought it was.
Starts in 1965.
It almost looks like the amount of support they have 24 is 5 higher on the
It might be a little bit how they actually broke it down.
But they're trying to say that it's at its highest.
Yeah.
Okay, so yeah, that makes sense.
But they're also not showing you anything previous to 1965, where it could be a lot higher or a lot lower. So it's like, it's just showing you, it's showing you a very specific thing. I think Facebook should mark this one with missing context. Why is it the case now? Yeah, it's like, why is it the case now? So there's a lot of interesting things with why unions are becoming a lot more popular today than they have been in the past. One more. Can't do graphs without showing you one from Trump. All right, here you go. I seriously was trying to find the one from Biden, the same thing. And I couldn't find Biden's. So
What is the same thing?
I think it was more just to show you. And, hey, at least they're not two different ones like one of the other graphs we've looked at. This is another one that I would say missing context. The graph actually isn't bad. It's yes, it should have gone down to 0 instead of starting at 22.5. I think these are actually millions of jobs in the manufacturing sector. Yes, that should be somewhere written on there. Oh, actually, no, it's not jobs. It's actually production rate. But they're showing it's at the highest point since 2018. Okay. Yeah, it's the highest reading since 2018. But really what they're trying to show is, hey, we flew up from down here when we shut everything down. Well, of course you're going to go up. This was from August of 2020 when it was like, yes, COVID's gone. We can start getting back to work. And then September hit and it dropped back down again. So it's like, again, so not all graphs are bad graphs because of the data. Some of graphs are bad because they're missing context. Some are bad because the way they're showing you it pushes one thing or another. So there's lots of ways that you can see bad graphs. Okay, so hopefully now when we start to look at the graphs and start looking, you can start to look at them with a little more keen eye and what are they trying to show you.
So if you were to give us a test and we've seen that graph and you put it in context, we'll get it.
Yeah, but I would honestly, depending on how you tell me the answer, like unless you tell me that there's nothing wrong with it or like there could be a lot. You could have told me it didn't go down to 0. That was also there's no break point there. That's another important thing. Like there's lots of different things you could have told me of why this graph is a bad graph. Missing context is a big thing. Like being able to explain what does this mean? Like you have no clue what the context of it is at all. So, all right. So like even this the one over this one that I showed you earlier, it's showing it in different pieces and different ranges. So it's like it's not necessarily bad because of the data or they didn't show percentages. It's bad because of how it's the way the information is presented is an appropriate use of a pie chart. So, all right. All right. Close that. We're going to stop the recording.